So we're continuing our understanding and our discussion of two theories that were necessary to start chemistry. One was the particle theory. Hey, there are little particles of matter, okay, that make all of things. And again, that started with our Leucippus and Democritus. Good for me. I could say it last period, now I can't. Any case, there is a particle theory. Leucippus, I can do it, okay? And eventually through the process, a mole theory. Now we need, of course, a particle theory of matter, that there was actual particles before we get to a mole theory. We should understand where I'm headed and why I'm going this way, because we've used this already in our first 5 weeks. We've used the idea that, hey, particles exist, and in fact, we can actually count them in a certain way to come up with ratios. In our electrolysis experiment, we noticed that in our test, if you do this right, Mn plus 2 gain 2 electrons to become Mn0. That's a 1-to-2 ratio you guys used in a calculation to figure out how many grams of the manganese you should have had. And a lot of people got that wrong. They forgot that in that calculation. So the ratios of 1 to 2, that's part of mole theory. Also, to figure out grams. How many grams equals 1 mole? We know the atomic mass is the mass of some number that's the same. Well, I need to explain that. Before we get that and use this, we have to establish that there is a particle theory. Because what are you going to count in a mole theory if you don't believe that particles or atoms existed? Okay, so that's where we're headed. Okay, and I know you did this last night or the night before or this weekend, but I want to go over the most important parts. So we talked about the Greeks, the geeks. These are the people that had time to think. 500 BC, Leucippus, which was the teacher of Democritus. I'm not sure which one, but somewhere along the line, they came up with an idea that there is a particle theory of matter, and they used the word atomos. Okay, little. I think it meant little. Particles or little indivisible particles, meaning that if you take matter and slice it up into small pieces, you come up with smaller little particles eventually that make up all matter. Now the reason I'm bringing this guys up is that you need to know that these were the first people who came up with the atomic theory or an atom theory or particle theory. But it was all based upon thought or logic. They had the time because their society dominated the landscape. They didn't have to worry about what was for dinner. But a really important part of these guys was that Leucippus and or Democritus, they thought in a way that was based upon the scientific model. Understand, the Greeks had their gods, and it's the gods that did this to us. And so the philosophy of these two men, and again, probably more so Democritus, was that they didn't look to the gods for answer. Their thoughts were about there was some underlying cause that all of the universe or their planet, and they didn't think about planet, but there was an underlying theory of nature. There must be some reasoning how nature works. And all we need to do is kind of observe and see why. Now, of course, that's really the foundation for the scientific model, okay? That you don't have the answers already, and the answers are out there. We just have to reason through what we see and observe, and understanding that there's some natural laws out there that is making things happen. So their perspective of logic was understanding that there was some reasoning based upon how all things worked. And it was through the eyes of the entire universe or the entire existence of what they saw in front of them. Their perspective was from the outside in. That's important, okay? And to them it made sense that all things are made up of the same indivisible particles. Now they had nothing to back that up with. Okay, but that was the first person that started the word atomos. Okay, nothing happens at random. Everything happens out of reason by necessity, which informs a great deal of Democritus' own writing, especially in his claim everything happens according to necessity, by some law of nature. Okay, has to occur this way. It's how it works. Okay, so again, the idea was from a outside looking in. I don't know where my cursor is, so I'll just click. Okay, well. Many consider Democritus to be the father of modern science because he's considered to be a materialist, believed everything resulted of natural laws. Now this was contrary to what Socrates, Plato, and Aristotle, the big three, the big philosophers. You hear about those three, you don't hear about Democritus as much. And so, as we know, Plato was a student of Socrates, Aristotle was a student of Plato, and Alexander the Great, although not a philosopher, a conqueror that created or founded the Western civilization as we know it, okay, was a student of Aristotle. So these big three individuals, okay, did not believe in the, didn't think in the way that Democritus or Lysippus did. They themselves thought from the perspective of the individual. If the individual, we are the center of the universe, and it's our perspective that matters, not some underlying cause of nature that we have to figure out. It's almost like the universe has to figure us out, okay? So their perspectives, although very good, I like some of them, there's only one good, knowledge. There's only one evil, ignorance. Boy, that is so true today, isn't it? I like that statement. He who studies how things originated and came into being will achieve the clearest view of them. So there's a lot of good things that they thought. I'm not saying what their thinking was abstract by any means. But their thinking was logic was from perception of the human being. Our logic was from our perception. Well, why would we think that things are made of atoms when we don't see them? Think about that. Why would we think that that if we take matter and slice it up into smaller, smaller pieces, why wouldn't we not think they would just be smaller and smaller, smaller pieces of the same thing? Why would we think they'd become up to little tiny? They come into little tiny indivisible particles that Democritus and Lysippus thought they would. Why would you? Okay, it's not from our perception of a human being that would be the case. Why would you create something that's not something we can actually perceive? We can't see it. It's not from our intuition. So there's no need to go that route. So because that was their philosophy, I believe, okay, that, boy, Western civilization as we know it didn't and had a hard time grabbing onto the particle theory. It wasn't until 1905 that the current establishment of scientists believed wholeheartedly that atoms existed. And that really prevented chemistry, okay, from working, because you cannot do any chemistry unless you can count particles or at least look at their ratios. We can't count individual atoms ever. But what we can do is we can have equal amounts of them and use ratios to figure out chemical formulas. Chemistry required chemical formulas. And chemical formulas we could use to predict how much we would make. Right now, chemistry was mixing stuff together and see what happened. It was not really a science until we had a particle theory and had some working way to count those particles into ratios. That's really important as we go through this. So, any case, I know you went through it by yourself, but I'm here to help you. Unlike Aristotle, Plato, Democritus tended to explain the world without reasoning as to purpose or from the human perspective. Okay? Democritus had been disliked so much by Plato that later wished all his books were burned. And so was the idea of atoms for over 2,000 years. Okay? There was a resistance, such a resistance to the particle theory. Unbelievable resistance, even when we knew there was particles. We were building steam engines, okay, in the 1800s, knowing full well particles created pressure to move locomotives. Yet people said, I don't think atoms existed. Now, Robert Boyle, understand his time period. Look at this. Early 1600s, to late 1600s, okay? This is the time where the church, the Roman Catholic Church, had its stronghold on the world, right? And you were a heretic if you went against the teachings of the church. And if you remember, during this time period, you had Galileo, who thought that from his observations using his earlier telescopes, that the Earth that we're on actually revolves around the sun, not that all of the planets revolve around the Earth. And of course, he was jailed, okay, for that, excommunicated, okay? So Robert Boyle, who was doing his research on gases, and what do we know about gases? Well, he has the famous Boyle's Law experiment. States that, hey, if you were to make the space smaller for a gas, the pressure increases so much that I can't push on that anymore. Now you take this off, goes in. If there weren't little tiny particles that made up air, okay, when I put this cap on, we should be able to do what? Push it through. But we know it gets increasingly harder and harder. In fact, at some point that cap's going to come flying off because the pressure is going to increase. make the space smaller for air or gas, the pressure increases. There's some force building up. What's that force? It's easy to what? Perceive. It's molecules or particles bouncing around faster as you give them less space to move. Okay? So his work with gases clearly showed that there must be particles of matter involved in creating these pressures and these collisions. But he couldn't come out and say it because, there's no what? There's no atoms, and again, he didn't want to be labeled as a heretic, he didn't want to be excommunicated, he didn't want to be jailed. So what did he do? He wrote a play where his characters argued for the existence of molecules. He didn't say it, his characters did in this fictional, play. It's called The Skeptical Chemist. And he outlined his research in this play, okay? He wasn't a theologian, he was a scientist, but he was so afraid to come out and say, this is my work and this is what I think, that he had to have a character do it for him. Okay, it's kind of interesting times, all right? But he laid some serious play that denounces the idea that atoms cannot exist. So it showed that atoms, at least from his work, there's got to be some particle theory. There's got to be particles moving around. All right? Any case, he further supposed that the elements were ultimately composed of particles of various sorts and sizes for his research to make any sense. Joseph Priestley, this was another researcher. He was a priest, by the way. Can you imagine that? He was also a priest. And what do you think the priests believe in? No heresy. Okay? Science according to what religion states, right? So he believed in what's called the phlogiston theory. The phlogiston theory. Now, the phlogiston theory is a theory that things that can burn have phlogiston in it. And then, when they burn, the phlogiston leaves. And that's why they're what? Lighter. And we know that air that doesn't have phlogiston in it, dephlogisticated air, will make things burn because they don't have phlogiston in it. When the air has phlogiston in it, things can't burn. And now what was his attempt in this crazy theory? It was his attempt to explain, that there isn't an element that makes the reaction go. There isn't an atom or molecules that do it. It's some phlogiston that's inside stuff. And when it leaves it, the air has it and that doesn't burn anymore. It stops the other. It was a crazy idea. He supposedly was the first to discover oxygen. Now, oxygen was his dephlogisticated air. It was air that didn't have the phlogiston yet, so it could support burning stuff, combustion. But once stuff burned, we all know that oxygen gets used up, or you have high amounts of CO2 in water, there's not enough of it to support burning. Put a candle underneath the container, the candle goes out because you do what? You don't build up phlogiston, you use up the oxygen, and the oxygen doesn't support what? You have no more oxygen to make a redox reaction occur, which is basically combustion. So it's a crazy, crazy idea that lived for 100 years to do what? Support the idea that there are no particles. And again, he was a priest. Interesting enough, And so, it's a crazy idea. So that instead of confirming that oxygen, an element made of particles, was an important chemical in supporting combustion, a redox reaction, it was instead explained that air with oxygen was dephlogisticated air. Once phlogiston left the fuel or wood, the air was full of phlogiston and burning ceased. Oxygen was air that did not have phlogiston and thus it's supposed to support combustion. There wasn't a particle responsible for the reaction, it was just some kind of stuff called phlogiston. So instead of supporting an atom-particle theory, he supported a concept that was ridiculous. And of course it's crazy. If we hold on to Aristotle's perception that matter was infinitely divisible, because why wouldn't it be from a human's perception, with no small pieces of matter making all things, particles, you had to accept the ridiculous phlogiston theory. And it lived for 100 years, because I think people were afraid to go against the priest, the church, But supposedly, this crazy idea also took the smart people, and they started doing research to say that this is so crazy, how can it be acceptable? So I talk about Joseph Priestley because his crazy idea to hold on to no particle theory really was a driving force for what? Those that believed in particles. This is so crazy to accept, there must be a particle theory, let's investigate. And that's where the other research was done, including Antoine Lavoisier. He was a tax collector. He's part of the aristocrats. He lost his head at the guillotine during the French Revolution because he was aristocrat. But he, of course, opposed phlogiston theory, okay, because it's not some weird stuff inside stuff that burns and gets released and it's part of heat. Okay, what he did very simply was he did a reaction. And supposedly he took some kind of reaction vessel that he could seal, and he would have a chemical reaction. I think it was mercury oxide, possibly. Any case, he heated it to make the reaction go, and he saw a physical change. He measured the mass of his reactants, and with heat in his reaction vessel, had something different happen. Okay, and he measured the mass of the products. Lo and behold, and under careful observations, he saw that there was no change. The mass of the reactants before the chemical reaction was the same after, which led him to believe that atoms or particles are just interchanging. He didn't come out and say it, but he came up with the law of conservation of mass. Meaning, if the same mass is in the products as reactants, possibly the same particles or atoms are involved. Atoms aren't being destroyed or created, they're just being interconverted. He didn't come out and say it, but it was strong observation. It showed it wasn't about heat being gained or lost as part of phlogiston. It showed that there was something inside these chemicals that was staying constant, even in the changes. And that course constant we now know is to be the atoms or particles. Okay? All right? So Lavoisier was able to establish that heat played no role in adding or decreasing weight, as had been claimed by the phlogiston theory. Okay, and this idea was decisively destroyed by the work of Lavoisier. So he killed phlogiston theory. Unfortunately, the guillotine killed him. It was mercury oxide. Okay, and this is very important. This is a missing mass lab. Okay, we'll talk about that. We do a lot of that in the earlier parts of chemistry, and that's what we're doing. It's a historical version of how this works. Mass of reactants, mass of products. Atoms are being interchanged. We now know in his experiment that a mercury atom and an oxygen atom were stuck together in chemical bond, ionic compound. And then, well, we had two of these, and they broke apart. And the same, there's two atoms of oxygen, two atoms of mercury, two mercuries, two oxygens, same number of stuff is there. He didn't know the chemical reaction. That didn't exist there. But his research opened the door. Now, Joseph Prost, this is where I'm going to stop today. Joseph Prost took a step further. Okay, law of conservation of mass. Great. So before and after of chemical reactions staying constant. Not sure exactly what that is, but what he came up with is he came up with an idea of law of definite proportions. Really, really important addition to what we're finding here. Phlogiston theory is dead, okay, for sure. So what he did was he took different pieces of the same compound. For instance, let's say he collected, okay, the rust of copper. Okay, we all know the rust of copper, okay? The rust of copper is copper oxide. Now we all know it looks like this. We know it's copper plus 2 hanging out with negative 2, okay? But they didn't know that then, okay? They just saw, hey, let's take this compound, it has a greenish blue color to it. Obviously it's the color of the Statue of Liberty. It's the color of, the patina of copper rusting. Now, they took this compound, we took this copper from different samples. He may have had some copper in the lab, copper outside, different places. He grabbed the same color samples from copper, the rust of copper, and what did he do with it? He heated it. And the idea of heating was to separate something from them. It's called a missing mass lab. Now, when he heated it, what he got back out was pure copper and oxygen gas, or as we say, dephlogisticated air, okay? Now, we now know how to balance. We now know if you need 2 of these guys, gives you this and this. They didn't know any of this yet. There was no chemical formulas. So what he had was the mass of his compound. Let's pretend he had 10 grams of it. He heated it. And if you don't understand this, I'm going to get heated. Okay? So he heated it. And he saw it change to pure copper. And when he massed the copper out, His sample was now 8 grams. He knew that oxygen left because he could collect it, and he saw that it supported combustion. All right? So the missing mass was oxygen. And of course, what must be the grams of oxygen? If it's 2, right? Antoine Lavoisier stated what? The mass of the products must equal the mass of the reactants must equal the mass of the products. So because of Antoine Lavoisier, it made him be able to build upon his research and said, hey, the missing mass of this oxygen, we now know it to be O2. He didn't know anything about it other than calling oxygen. We now know it's that. We didn't know this. All he knew was this. Hey, 10 grams became 8. The other stuff just left. It got lighter. Something left. Not phlogiston, oxygen, because he could collect that gas that left, and he could see it supports combustion. So we know oxygen left. But all he had was, he didn't have any of this, didn't have any of this. He just had 10 grams going to 8. And he concluded, because of Antoine Lavoisier, that when I do my percentage, part over total times 100, what's the part? Take the total mass of my compound, and he got 10 grams. Take the missing mass. He knew that it went to 8 grams. So it must have been that 2 grams of the oxygen was part of it, based on Antoine Lavoisier. Because of there's no what? Change in mass, the mass must be conserved. He had 2 grams. Times it by 100, and what he came up with, a 20% by mass of oxygen in this compound. He didn't know it was copper 2 oxide, it was copper something. He may have named it, okay? They may have some common name. So what did he find? Now, I'm making this number up, okay? But what I'm trying to tell you that when he took different samples of this copper rust from different places, he always got 20% by mass of oxygen. He went as far as another country to get copper and brought that compound back, and he did the same experiment, got 20%. So it led him to believe, because the percentages were constant, if his starting material was pure, it led him to believe that they're made of the same amount of copper and oxygen. Now, he didn't know, he didn't say it's the same number or same different atoms, but now we know something. Copper oxide is what? 1 oxygen to 1 copper. Always. Chemical compounds have a definite ratio of atoms and types of them. Water is what? H2O, always. He was the first to discover that chemical compounds have unique chemical formulas. He didn't know about chemical formulas, he didn't discover chemical formulas, but his research led people to believe that there was an exact ratio of atoms because the percentages always stay constant. If copper oxide could sometimes have different amounts of oxygen, this would be different. So his percentages by mass of the element missing, and knowing it was one element, and using multiple samples from different places, led him to believe that copper oxide has the same amount of oxygen in it always. When it's not copper oxide, when it's copper and something else, it's going to have a different percentage, meaning there's a different arrangement of atoms. That's big. He built upon Lavoisier. Okay, big. I'm big. Okay, here's an example of lead sulfide. He had 100 grams of lead, heated it, sulfur came off. It disappeared as sulfur gas, stinky gas. That's what's left. So you can figure out how much was sulfur, and so forth and so on. The bottom line is the percentages that he found, okay, were always constant. So, always constant if he had the same compound. If the compound was different, the percentages were different. Meaning there was different what? Atoms. What made a compound unique was it's a unique amount of the other atom. Okay? The only way that he could express this other way was percent by mass. And that's our first lab, a percent by mass lab. Percent by mass opened the door for us to believe in particle theory and put together chemical formula. It was the percent by mass that did that. Okay, and that's where I'm going to stop. Because from the percent by mass, law of multiple proportions, Antoine Lavoisier, who set up percent by mass, and many other people who contributed, John Dalton put that information to say, wait a minute, the reason why these percentages are staying constant, the reason why the masses stay constant, is because they're made of atoms. Okay, and he brought back the modern atomic theory. Okay, so I'm going to stop here and talk about our first lab. All right, so let's cancel this out, and let's go to this right here. I don't know my, there we go. Let's go back, and let's play it. Let's pause it. Now let's not see my other videos. Okay, so what is this about? What's our first lab? Well, how dare I not connect you with what we learned? We've been learning about what? Crystals, either of metals, face-centered, body-centered, simple cubic structures, okay, ionic structures. Okay, well, I'm going to bring for you a new structure. We have copper sulfate. It's a salt, and this is a 3D representation. So copper sulfate looks like this. Copper and sulfate. We write this chemical formula. It's a lie. It's ionic. Copper is +2. Sulfate is SO4. This cluster of nonmetals is -2. And they stick together because of ionic bonds. And this goes on in all directions. It's a salt. We're used to what? Like copper chloride, sodium chloride. But this is a what? Polyatomic ion. It's a cluster of bonded chemicals that has a charge, so it's in the crystal. It has the same basic structure. I mean, we're looking at whether it's NaCl or copper sulfate. Now, if you look at the crystal, let it rotate. Where am I? This brownish orange thing is the copper, and the sulfate is SO4. So I know it's hard to look, but the sulfur is this yellow. You got 1, 2, 3, and there's another one behind it. So the sulfate is right here. And it's attracted to this copper. And if you stop this and look at it more carefully, there's 1 copper for every 1 sulfate. Hard to look at it this way, but you can see that there's that 1 sulfate to 1. 1 to 1. It's a 1-to-1 arrangement, okay? Little complex to see, I get it, okay? But that's the salt. Now we call this an anhydrate. Reason is, has no water. A lot of salts come together and form a crystal in water. Not because they precipitate, because the water evaporates off. When the water evaporates off, these guys come together, even if they're soluble, back into a crystal formation because there's no water to pull them apart. But sometimes that water gets inside, and it does here. So let's get rid of this, and let's play this one. So this is the same compound, but now we have water molecules. Here's our sulfate, SO4. There's a sulfur, and there's another sulfate here. And it's attracted to 1 copper. But now here we got the water molecules. I'm going to stop this just to make some sense to it. Ooh, that was the part I wanted to stop it. Christmas. One more time. Okay. So you can see the arrangement. There's a sulfate, there's a copper, okay? And then you have the water molecules. The red is the oxygen. If you notice, the water molecules are not haphazard. They're in a particular place in the crystal, kind of like an interstitial alloy. They fit inside, but there's something really cool about things, hydrates. Hydrates are the salts with water. We write them this way. A dot means with. We write the word water, we put 5. We have found that copper sulfate, when it's a hydrate, has the water in it, there are 5 water molecules for every 1 copper ion and 1 sulfate ion. Why? Because they fit in a particular arrangement. There's a particular arrangement they fit. It's not haphazard. So they're kind of like part of the crystal. They found a place to be orientated. Okay? And why would they do that? Well, think about it. You have a positive part of water here, the H, the negative part of water. The negative is going to attract the positive copper, and the positive attracts. So they find a place. And we now know the chemical formula of this salt is copper sulfate pentahydrate. In fact, we call it copper 2, Roman numeral 2 from the summer. It's Roman numeral 2, it's plus 2 or plus what? Plus 1, right? And it's penta for the 5, and it's a hydrate. It's telling you there are 5 water molecules. Now, this is a lie too. This is telling you the lowest ratio of what? Stuff in this crystal. Now, what are we doing with this? How'd they find this out? How'd they know there was, okay, an exact number? We do a missing mass lab. You know what they do? They take, and this is what we're going to do. They did what the Prost did. You take your hydrate. It's a fancy word for the salt that has water. In this case, it's copper sulfate, copper 2 sulfate pentahydrate. Now we're going to be using this knowing there's 5 water molecules. I'm going to tell you that. The next lab, you're going to discover that. We're going to apply some heat, just like Antoine Lavoisier did. And what we're going to do is we're going to take these water molecules, and with these water molecules, by applying heat, they're going to evaporate out of the crystal. They're going to leave. So you're going to make 5 H2O gases. Okay? And what remains? The dried form of copper sulfate. Notice that's a plus. This was all together. We call this guy the anhydrate, the dried form, the anhydrate. This, of course, is water. Hey, if this is 10 grams, we know that the product of the anhydrate water have to be 10 grams. But if after I've driven off the water, there's 7 grams, how do I find the percent by mass of water?
3 grams over 10 grams?
Right. Part of the water, which is going to be missing, over the total mass of the hydrate times 100. So it's going to be 3 over the total. So we get the 3 grams by subtracting what we get after we drive it off. Over 10 equals 30%. And if we do this over and over and over again, and use different copper 2 pentahydrate samples, we always get 30%. Why? Because copper sulfate pentahydrate always has this definite proportion. It has exactly that amount of stuff always. Okay? So that's what we're doing tomorrow. Have a believable day, everybody. You have a homework that takes us a step further. We get percent by mass, but we actually get the ratios. Ooh, that give us the chemical formulas. See you tomorrow.